Hey guys, it's Chuck here. I've been asked by a couple of different groups if I could do a few quick reviews for folks that could be recorded into small snippets where you could review it online on your phone, wherever you may need to review it. So what I'm going to do is I'm going to go over some super important concepts in the theory of ventilation, circulation, when taking care of patients in general. I'll cover baseline and then we'll get into some of the disease processes, but I'm going to try to keep all of these videos roughly 5 to 6 minutes long so that you can take them in, digest, rewind, do whatever you need to do with them. And we're going to start with the first one here, which we're going to talk about ventilator therapy, but this is going to be about VQ matching, and I'm sure that you've heard the term before. So anyways, today is April 2nd, 2020, and we're in the midst of the pandemic, and nobody knows how long this thing is going to last. Hoping it burns out soon, but in the meantime, we know that these patients come in with this profound hypoxia, and they're really doing some work in order to breathe. So we want to make sure that we're doing the best that we can to manage them, and one way that we can do that is having a pretty good grasp on basic concepts. So anyways, let's start with simple perfusion. So I'm going to go over cardiac output real quick. If you've taken a class with me before, you've heard this. This is the cornerstone of a lot of what I teach. Okay, and when we talk about cardiac output, we talk about heart rate times stroke volume. Okay, heart rate times stroke volume gets measured out in cardiac output, and we typically measure that cardiac output by the minute, and we measure it either by milliliters, cc's, or liters. Typically, we measure by liters. So anyways, the happy, healthy, normal heart beats somewhere around 70 beats per minute. Okay, we know that that range is somewhere between 60 and 100. And we know that the stroke volume on the average healthy, happy heart is somewhere around 70 mLs. Okay, that doesn't mean that you can have more. That doesn't mean that you can have less. It means that that's kind of the average that we're looking at. So the average person walking around with a normal average heart rate and a normal average stroke volume is 70 times 70. Okay, so 7 times 7 is 49. There's two zeros there. It's 4,900 mLs per minute is what you're circulating. And hopefully that's oxygenated blood. If you're breathing, if you have a VQ match and you're breathing and you're oxygenating, this should be normal oxygenated blood. Okay, another way to write this would be essentially 5 liters per minute. Okay, if you really want to get accurate with this one right here, okay, what it would be is what? It would be 4.9 liters per minute. Okay, and we know that that can range, the average cardiac output can range anywhere from 4 to 8 liters per minute. Okay, hopefully that makes sense. It's something that we all learned way back when. All right, it's part of the basics. Okay, so let's see how that works. You get on the treadmill at the gym and you start running and your heart rate goes up to 100. Okay, your stroke volume stays roughly 70. What happens to your cardiac output? It goes up. You have a higher demand. You need to get oxygen to the tissues. One of the ways that you can do that is you can increase your heart rate. And now you're moving 7 liters per minute. Okay? In order to do that, in order to oxygenate all that tissue, your respiratory rate's going to have to catch up to your cardiac output, your tidal volume, your minute ventilation, etc. And we'll get into that in just a moment. But this is a real important concept. If you go into cardiac arrest and you go into VFib, your heart rate is 0, which means that your stroke volume is 0. What is stroke volume exactly? Okay, it's not EF. Ejection fraction is something different. The ejection fraction is how much blood is pumped forward versus how much blood is left behind in the ventricle with each contraction. The stroke volume is the total amount of blood measured in cc's moving forward each time that left ventricle collapses on itself. Okay, and we said that the average is 70 mLs. All right, and this here in VFib, you'd have 0 times 0, which gives you cardiac output of 0. Okay, now part of the issue in cardiac arrest that we're going to talk about real quick is that we come along and we do compressions at a rate of what? Has to be greater than, okay, or equal to 100. We really look for that 100 to 120. Well, the issue is this. We know in cardiac arrest that we only move about 20% of normal blood flow, which is 1 liter per minute, if the average is 5 liters per minute. Okay, so where's our problem in cardiac arrest? It's not the heart rate. Yep, it's the stroke volume. That becomes problematic because instead of 70 cc's, we're only moving 10 cc's each time we do a compression. Okay, so hopefully that makes sense to you. Let's tie it together real quickly, okay, and then we'll move on. So we're going to call this Q. Okay, so you've heard of VQ matching. Q is perfusion. The V side of that, okay, which we can actually write as V, or we can write it as minute ventilation, is how much gas we move in a minute. And how do we get that measurement? It's really simple. Okay, heart rate, we're looking at respiratory rate. Stroke volume, we're looking at tidal volume. Okay, and that's going to give us how much gas we move in a minute. What's the most common vent setting that you guys typically see? Okay, and how did they come up with that vent setting? I'll show you. We've got a heart rate of 70 times stroke volume of 70 equals 4.9 liters per minute, right? We want to match that, okay? So how do we do that? Well, the average healthy resting breathing rate, right? Most of these folks want to go with 12 breaths per minute. And the other setting that we see all the time is 500 mLs. So when we look at that 500 mLs, that's about half a squeeze of an adult BVM bag. They're typically a liter to 1.2 liters, okay? But 12 times 500 gives us what? Gives us 6 liters per minute. That's basically, okay, the easy way to look at this, that's a match. I know 6 doesn't equal 4.9. There's a reason for that, okay? This is the reason. We have something called dead space, okay? So I know these are drawn to scale, beautiful art. Anyways, when we talk about dead space, this 500 cc's, that's the total amount that the vent is going to deliver to the patient, okay? The issue is this, is that we know that gas exchange only happens in the alveoli. That's where you get the O2 in, and that's where you get the CO2 out, okay? That's the only place that gas exchange happens. It doesn't happen over the total 500 cc's, okay? What we need to figure is something called dead space. Dead space is this area right here. This is the trachea, this is the bronchi, this is all the areas that don't have alveoli, okay? And some estimates count that dead space. This is the area right here that we're talking about, the dead space. It includes your sinuses as well. Some estimates say on a 500 cc tidal volume, roughly 100 cc's, okay, 100 cc's to 150 cc's is dead space. And basically all dead space is it's the amount of volume, it's the pressure, okay, that creates that. What you're looking at is you're pushing so much volume of the gas down into that dead space to get gas exchange at the alveoli. So I have to fill this area right here with 100 to 150 cc's in order to get this right here, gas exchange, okay? So let's look at why this number is actually considered a VQ match. Because if I'm breathing 12 times a minute and I take 100 cc's off of that breath every single time to fill my dead space, okay, 100 cc's goes away here. 100 cc's times 12 equals, okay, 1.2 liters, all right? Or 1,200 cc's. You can write it any way you want. But if I take 1.2 away from 6, what do I end up with? I end up with 4.8 liters per minute. There you go. There you go. There's your match. That's what we want. Hopefully that makes sense. And we're going to end it right there and pick up on another section.